because I did a change. Or no?
Yes, we can see.
Yes. Okay, thank you. Perfect. So yes, that is the work I am going to present, and I also want to give credit to all the other authors. So here it is Rafael Vasquez, which is my PhD advisor, and also James Biggs and Franco Bernelli, who were hosted me at Politecnico di Milano when this research work was done. So we will go to the introduction. And actually, the introduction and my motivation for this work, I think that a lot of things have been said during the workshop. So the main motivation is that very limited data of asteroid properties is available if we have not visited the body before. And actually, from the point of view of guidance and control, this is a problem because we don't know the gravity field. So my objective is to maintain a bounded orbit, and I will explain then why, with the stationary attitude, while I undertake the in-situ estimation of the gravity model parameters. So our methodology will be to develop an Unscented Kalman filter combined with model predictive guidance and control. And we will also explore the use of a satellite constellation, and we will see that it enhances the gravity estimation. So yeah, that is one of the cases, and there were others that were said during the workshops as a Rosetta. But Ultima Thule, until New Horizons did a flyby, there was a lot of speculation about the shape of the asteroid. So it could be a binary asteroid. They didn't know if it was a bilob asteroid, that it turned out to be. And also it could be an elongated asteroid, they didn't know. And finally, yeah, it was a bilob asteroid. But still, until you are very close to the asteroid, you don't know what shape you will find. So that is also a problem, because if I don't know the gravity field and I try to follow a Keplerian orbit, and these are two cases where the initial orbit was circular and I did not control anything, well, the left figure ends up in a collision trajectory with the asteroid, and the second figure ends up with a escape trajectory from the asteroid. So that points to the need of control. There is also the concept of frozen orbits, but if I don't know the gravity parameters, I cannot target those. And also from the navigation perspective, the optical devices of the spacecraft are required to be stationary, so they can point to the asteroid surface in the optical navigation, because it's the navigation system I was considering. So I will start with the dynamics then that I've been considering. And yeah, we have 4 reference frames of interest. One is the inertial frame in blue. The other one is the asteroid frame which rotates with the asteroid, which I am just considering that it's a classical asteroid that rotates along its semi-major axis, and the rotation is uniform. Also, we have the orbit frame, which evolves with the spacecraft along its orbit. So it is pretty convenient because the x-axis line always points to the asteroid center of mass. So that's why here I have drawn the body frame, because I want to maintain the body frame stationary with respect to the orbit frame, so I can point my optical devices to the asteroid surface. So in orbital dynamics, I am not entering too much in this, but what I am going to use is modify equinoxial elements, because they avoid a lot of the singularities arising with classic orbital elements. And there is also the Gauss variational equation for this type of state, which is this equation that I am not writing because it's pretty big. And what you need to know is that it is a nonlinear function of the modified equinoxial elements itself and the perturbation acceleration. So in the perturbing acceleration, we can decompose that into non-Keplerian effects and the control that I am applying. And the non-Keplerian effects, this is the only force I am considering, is the gravity field inhomogeneities of the body. I'm not considering solar radiation pressure or Jatkowski effect or any other type of perturbation. Then I have to also characterize the attitude motion. And well, I will use modified Rodriguez parameters because I am a big fan of them, and they are very suitable for guidance and control also. And they have a kinematic equation, and also there is the Euler classic equation of dynamics for the attitude, where J is the inertia matrix. I also have the torque T, and the torque will be composed of the gravity gradient and my control. The gravity gradient, what I am doing is assuming a very simple model. So I assume that I have a point mass model of the spacecraft, and I just do a summation of every individual contribution of each point mass to the torque, and yeah, and also considering the inhomogeneities of the gravity field within the gravity gradient torque this way. So then we are going to see what we have done for the navigation. The first thing is that I am not an expert in sensors, so I am not entering very much in the detail of how they obtain their output, but I will enter in just the filter. So my objective is to estimate the modified equinoctial elements, the modified parameter, which is the attitude of the spacecraft, the angular velocity, and these two are the gravity parameters that appears in the spherical harmonic expansion. So these are the spherical harmonic coefficients, C and S, which characterize the gravity field. And also this is the gyroscope bias. That is something that you have to estimate in order for the gyro to be trusty, and you can use it. So for the typical devices, I will just consider a simplified way a LiDAR and a camera. So it turns out that a LiDAR and a camera could allow me to have relative position vector between my spacecraft and this asteroid surface landmass. So that's the input to my navigation filter. And then I will consider for the attitude star trackers and gyroscopes, which is a classic solution. So they will give me the attitude, will be provided by the star trackers with respect to the inertial frame. And the gyroscope will provide also the angular velocity, which is my angular velocity with respect to the initial frame. So why I'm going with an unscented Kalman filter? Well, for the sake of autonomy, you have to rely on sequential filtering. And when you look at the literature, there are like three state-of-the-art estimators. So the left one is the one that is the particle filter, and is the most accurate, but the computational burden is high. So basically you have an initial statistical distribution that you have to pass through a nonlinear function, f, and then you have to, this is what is propagating your orbit state or your attitude within the filter. So you need to do that because between the time between measurements, you need to check out with your model how you're going to check the discrepancy between your model and the measurement. So the good way to do that is just to roll the dice as many times as possible, and yeah, you will get the complete full statistical distribution. So, but this has a high computational burden. So there are alternatives like the standard Kalman filter, which it turns out that is also linearized. So it introduces a lot of linearization error, and you can see that the final mean and covariance can differ very much from what is the actual one due to that. So the unscented Kalman filter, what is doing is a balance. So it just propagates on strategical points, which are the sigma points, through the nonlinear function. And it turns out that these statistical points just suffice to reconstruct in a better way, in a more accurate way, the actual mean and covariance. And that is why we are using the unscented Kalman filter for this purpose. And basically what I have is an instant Ti -1. I have the standard state. Why it's a standard state? It is because I'm not considering only the orbit state, but also the gravitational parameters. And I will, at some point Ti-1, I have its mean, its covariance, and also the process noise. Why the process noise? It is because I don't know, since I have unknown parameters, I have to estimate also the process noise in order to work well, because it's not like the sensors where you have a data sheet and you can, you know very well how the covariance of your sensor. And it enters a measurement set at TI, and using the Unscented Kalman filter, and at TI, I could estimate, I will give a new estimation of the mean, covariance, and process noise. So how are we treating the filters? Is that we will separate orbit and attitude, because they were at different frequencies, but they will share their gravity estimates. And we will see that later. And this is also because the attitude filter through the gravity gradient Tor also requires the orbit estimation. And why we were interested in working with Constellation, it is we consider not only a single satellite orbiting the asteroid. If we consider more, they could share their information about their individual estimation. So you could, in a very simple way that we did, but probably there are other options, we can average the gravity estimation that each satellite is doing. The intuition is that since each satellite could overfly different regions, the average will take into account a lot of information and will prevent bad behaviors such as outliers, and it also speaks convergence. And then I will go to show you how we design the guidance and control. And yeah, well, the objective of the guidance is just to compute a reference trajectory, and I will like it to be as natural as possible, so I don't do unnecessary control. And the control actually, what it computes is the control commands in order to track this generated trajectory by the guidance algorithm. So in my case, my goals are to station keep up on the orbit. I want to maintain constant semi-major axis and eccentricity. And I also want a stationary attitude with respect to the orbit frame. So it turns out that in terms of modified equinoctial elements, I just have to maintain 3 parameters constant, which are P, F, and G, and they are related to the semi-major axis and eccentricity. And then for the attitude, what I want to maintain is my modified radius parameters, constant, describing the attitude of the body frame with respect to the orbit frame. And this is the guidance approach, and I'm not entering too much into it, but what we have considered for the sake of computational efficiency, because every time you have to compute the guidance not only once, but and some frequency, because as you know better, the gravity. So we assume this as a fictitious quasi-natural approach, which is assuming that the control will be null. And I will assume that the control variables are actually controlled, which is the purpose of the control. So I will assume that in terms of that semi-major axis and eccentricity are constant in the guidance to its nominal values. So what's left? So I need to integrate the parameters that are not controlled, which are the other modified equinoctial elements, which are H, key, and L, assuming the previous assumption. So this will lead me to a time variant of the reference, which is not true, because when I will apply control, I probably will change H, key, and L in a different way. But yeah, this should be very close to the reality. And also the same will apply to the attitude guidance. I will assume that the applied Tor is constant and that the modified radius parameter is constant. So this will give me the desired angular velocity evolution. And then how I am posing the control problem is that I will define the tracking error, which is the discrepancy between my actual state and the reference. And I will pose this optimization problem through an integral form, which just balance the tracking error and the control effort. And this is subject to the tracking error dynamics, bounds in the control. And also there is this constraint for the orbit case, and our intuition was, and we demonstrated it, that since we are controlling semi-major axis and eccentricity, no out-of-plane control was required. So I have to transform the previous continuous optimization problem to a finite tractable form to be possibly embedded on board. So what I am doing first is I linearize the tracking error, assuming that my actual state, and this applies both for the orbit and the attitude, will be very close to the reference ones. So I obtain a classical dynamical system, A times x plus b times u plus x and derivative of the reference, because the reference, as I have told you, is fictitious, so you have to counterbalance it also. And this can lead to, you can integrate this linear time variance system through the state transition matrix, and you can obtain an expression literally of the tracking error itself. And then when you have that, you can discretize in n intervals of delta t. So you can consider a finite control horizon where you are applying for in that way. So you have now discretized the continuous problem, and then you can use, this is an easier compact formulation just to stack variables, all the discretization variables, and you can pose the control program to a quadratic programming form where there are very efficient solvers that can solve this problem. So yeah, and here is how I will obtain my control sequence for my control horizon. Yeah, this is the full scheme. And yeah, we have parts that we don't control, we are not, we have in yellow the dynamics. We have in orange all these sensors, and as I said, I'm not entering into the detail of each sensor, how they obtain their measurements. And also here we have the filters, the attitude UKF and the orbit UKF. And as you can see, they are constantly changing their gravity estimation. And also the attitude UKF requires the orbit state. Then this estimation and the gravity estimation goes to guidance and control, and guidance and control will provide a control torque and a control acceleration. And this works for each of the satellites. Yeah, so that's it. Now we are going to the results. We will consider asteroid Eros with a 14-order gravity model. Why this asteroid is because there is a lot of information from the NEAR mission. So it's like the benchmark for guidance, navigation, and control in asteroids. And I also considering that, okay, the reality is infinite, so I have to limit to a certain extent what the orbit filter and attitude filters are estimating. So the orbit filter will estimate up to 4-order gravity and attitude at 2 seconds. So there is a model mismatch also inherently in that I can consider a reduced gravity model for the filters. This is sensor datasheet that I am considering started for other research work that have considered similar errors. We try a gravity gradient stabilized configuration for the satellites, but it turns out that in asteroid, gravity gradient does not work due to the inhomogeneous gravity field. It does not work in the same way as Earth, but yeah, we just tried this configuration. And then these are the constellation scenario that we consider, and basically these circular orbits. Eccentricity, my reference eccentricity is 0, and then I have an X space, the semi-major axis by 2 kilometers, because I am not considering any sort of relative motion control between them. That is why I'm talking about the constellation, because I'm not controlling the relative positions. So this is a simulation that with the case of the 9 satellites constellation. That is the one. So you can see that, okay, the satellite does not escape the asteroid, does not collide with the asteroid. And the effect that you can see is that the orbit plane is, except for the polar orbit, which is the red one, the orbit plane changes accordingly to a non-Keplerian orbit because it is a free parameters. I mean, the inclination will not change, but the right ascension of the ascending node does change, and that is why I think like the plane is precessing in that way. Then results in terms of semi-major axis and eccentricity show that they can track the the desired values of each one of the satellites, and also the centricity is reduced to 0 because there is an initial crisis at the beginning due to the convergence of the filters. Then we have the inclination, and the inclination is you do not do out of plane control. The inclination is almost constant, so that is also a good way to also secure that you overfly each satellite is overflying the same regions. And here at the right, we have the second order gravity estimation. And the second order gravity estimation looks very fine. Then I will show you some numbers. However, when we go to third and fourth order, some of them, yeah, they look fine, but some of them there is some offset between their reference value, their real value, and the estimated value, although there is a tendency to track the gravity at least. So yeah, that's also the attitude of the satellites, and yeah, it's pretty well maintained in terms of yaw and roll to 0. But the pitch, we have an offset, and the offset intensifies as you orbit close to the asteroid, and yet this will require further investigation. But still, the offset is just in the worst case 2.5 degrees, so I mean it could be also acceptable. Then we have compared the Constellation results in terms of gravity estimation against single spacecraft, and we have found in terms of the second order gravities a great enhancement in terms of accuracy, which is this column, and the other column is convergence. So we consider convergence where the error is below 20%, and that's it for the second order gravity. And you can see that the Constellation, in average, reduce a lot the monolithic error and convergence time. For higher order gravity, it turns out also that the Constellation is more convenient, and even in that case, we have some problems with the monolithic configuration. We're just considering individual spacecraft to undertake gravity estimation that some of the parameters does not converge, and yeah, the Constellation configuration was successful to do that. So just when you pass from one satellite to 3 satellites, you see a great enhancement in the gravity estimation. And then I will just finish with the conclusions and possible future extension of this work. And yeah, our feeling is that we have demonstrated an autonomous, because I am not relying on ground in the loop algorithms. We have proved them as feasible. And we also have shown that the Constellation concept can significantly enhance gravity estimation. And again, we also have seen that second order gravity is accurately estimated, while the other higher order terms are poorly inferred. And we guess that it is because of model mismatch. As I told you, I was considering the full Spatium series up to the nearshore maker output, while I was inferring a reduced model up to 4 order in the orbit filter and second order in the attitude. Future work will include exploring alternative estimation technique, because Unscented Kalman filter at the end of the day is a state-of-the-art technique. So we would like to, I don't know, go maybe for neural networks, but I know that that will require some kind of batch processing somehow. And also, we would like to robustify the control, because we have a lot of statistical information, and we are not using it explicitly in guidance and control. And yeah, thank you. That concludes my presentation. Thank you for your attention, and I will do not hesitate to ask any questions.